Hey, this is Mr. Warden. This is the PreAlgebra Do Now 36.1 video key. So let's do this. So we are going to try to propose an approach to find the shaded area. And yes, you can assume that this is a square. You can assume that these quarter circles are quarter circles. Same with these two. And then you can assume the side length of the square is 6 centimeters, which means the quarter circles have a radius of 3 centimeters, and that this high pointy bit here is right at the center of the square. In fact, I will draw a line to indicate that here. It's going to be the most amazing straight line you've ever seen. It's actually not bad for this tool. Okay, so there, I have made that straight line right across. So what's a strategy for doing this? Well, it turns out very simply. So you could do a lot of things. You could figure out, okay, what is the area of this rectangle and subtract, so it's 6 times 3, so it's 18. And then you could subtract these two quarter circles. Or you could find out the area of this rectangle, and actually you could just find out the area of these two quarter circles. Okay, well, it turns out that since you're subtracting two quarter circles from this rectangle, then, so you end up with these two quarter circles being, and then you've got a piece of this rectangle that's removed. So you really just need these two quarter circles. Over here, you need this rectangle minus these two quarter circles. So overall, really, we're putting these two quarter circles back in from the rectangle that we removed two quarter circles. So you're not going to have to deal with any quarter circles at all in the area of calculation, because we can just take this quarter circle here and move it up here, and it fits right in. And this one will also fit right in. And so now we just need to worry about the rectangle, which is 3 centimeters by 6 centimeters. We just need the top rectangle, because that will be the area of the shaded bit. So it's 18 square centimeters. Okay, let's keep moving. The next question I'm asking you, as the number of sides of regular polygons increase, what would happen to the ratio of the perimeter over the distance across the polygon? And as you might notice, the perimeter, the polygons become closer and closer to circles. So what should happen is the ratio of perimeter over distance across should approach pi. That's what it should head toward. It should get closer and closer to pi. Okay, now when we consider what how we work out the distance across a regular polygon, a measurement like a diameter, well, we got two things we can measure. So this thing is called a radius, and it's called a radius. It's actually the radius of the circle that goes right around the polygon. It touches all of the vertices of the polygon. We call it a circumcircle because it circumscribes the polygon. And the apothem goes to the midpoint of the sides, and it happens to go to where an incircle, a circle that is inscribed in the polygon, exactly touches all of those midpoints. And so the incircle has a radius that's the apothem, and the circumcircle has a radius that is the radius of the polygon. Okay, so what we have to consider? Well, the long distance is double the radius, and there's a short distance that's double the apothem. And of course, there's you could combine radius and apothem and get sort of a middle ground, roughly speaking. But as you work this out, you would end up with a perimeter that's divided by a thing that is larger than and you'd end up with a perimeter that is divided. So one of the ratios, I should say, is going to be larger than pi, and the other one is going to be less than pi. But as we increase the number of sides of a polygon, those two numbers should get closer and closer to pi from either side. And I think that's a good place to start.